This is video 4 in the lecture on BMS safety. In this video, we'll discuss DFMEA, or Design Failure Mode and Effects Analysis. An important difference between FTA and DFMEA is that fault trees omit the severity and probability of events, while DFMEA includes these assessments. Neither tool is better or worse than the other. They are useful in different ways. Fault trees produce a more readable output, which is valuable for design. DFMEA provides greater coverage, which is valuable as a final check. If you were paying careful attention, you might have noticed that I mentioned FMEA and DFMEA and wondered about that letter D. FMEA can be run for various aspects of creating a product. Design FMEAs are used to assess a design. Process FMEAs are used to analyze a process rather than a product. In the following slides, I'll focus on DFMEA since we're talking about designing a BMS. Some people list yet more types of FMEAs, though I'd argue that these are all subtypes of design or process FMEAs. For example, a manufacturing FMEA assesses the manufacturing process, and a software FMEA assesses the design of a piece of software. All types of FMEA analysis result in a table like this one. In the rest of this video, we'll see how to fill in such a table and what the various headings mean. Let's do an example DFMEA for a battery switch. In the first column, we list the functions that our product or component must perform. For a battery switch, that might be that the switch opens and closes and precharges. And if you don't know what that means, go back to the BMS functions lecture. A complete DFMEA will fill out all the columns for all the rows. For this example, let's zoom in on the first function, opening. For each function, write out its requirements. Perhaps obviously, a switch should block current when asked to open. All switches have a maximum voltage that they can block, and that value is an important design spec. The switch opening time is important. Perhaps we include a reliability spec, the design lifetime in terms of number of opening times. For each of these, we next write out all the failure modes. Let's again zoom in on just one. For each requirement, write out the failure modes, or the ways in which this failure could occur. For a battery switch, a common concern with contactors is that they weld shut. A welder works by using a high voltage to create an arc across a small gap. That pretty much describes the moment right before a contactor closes or right as it opens, a high voltage across a small gap. A control signal failure could cause the switch to fail to open. And manufacturing imperfections or insufficient design margin could cause some switches to be unable to withstand the required 500 volts. Let's zoom in again. What is the effect of a battery switch welding shut? If it's permanently shut, it cannot open. And now, we arrive at the first numerical rating. We need to assign a number representing the severity of the failure. Severity is defined as a ranking number associated with the most serious effect for a given failure mode, based on the criteria from a severity scale. It is a relative ranking within the scope of the FMEA, and is determined without regard to the likelihood of occurrence or detection. Here is an example of a severity scale. 10 is the highest ranking. For a vehicle, a severity 10 event might endanger the lives of the occupants. The lowest rating, a 1, has no effect on the product. Consider now the failure we're discussing, that the battery switch cannot open in an electric car. To assign a severity, we must consider all possible vehicle states where this fault matters. If the car is parked or even driving, there's minimal impact evident to the customer. I'd call that a 2. If the car battery is discharged down to 0%, the contactor should open to protect the battery from over-discharging. But if the contactor cannot open, then this function will not work. This one is tricky. If the car gets to 0% and we don't protect the battery, most customers will be dissatisfied. But most customers don't discharge their cars to 0%. So, I don't know, 2 or 4? Now, consider what happens after an accident. contactors should open after an accident to protect first responders in case some part of the high voltage system has been damaged, shorting to some other part of the vehicle. In this case, the battery switch being unable to open affects safety without warning. So, for our table, I would write down a severity of 10, since that's the worst impact of a battery switch being unable to open. And there's that 10. Next, list the cause or causes of failure. Arcing across the contactor can cause it to weld shut and be unable to open. Arcing happens if we have a voltage across an air gap, which can happen if the contactors are closed without pre-charging or if they open while current is flowing. Arcing causes pitting in the metal, and contactors damaged like this are at increased risk of welding shut. Next, we assign an occurrence rating. Occurrence is a ranking number associated with a cause of failure based on the criteria from an occurrence scale. It is a relative ranking within the scope of the FMEA. In my experience, this is the most hand-waving part of the process. We're guessing how often this failure might occur. Recall that we're doing a DFMEA, where D stands for design, so this analysis occurs in the design phase of a product. Production follows, and only then do we see the actual rate of field failures. Here's an example of an occurrence scale. 10 is the most common, and 1 is very rare. If we're using a part that was previously used in production in another product, we might be able to look up the failure rate. If not, we might guess from whatever lifetime testing was done. For this example exercise, let's rate this a 2. There's that 2. Next are process controls, which are the tests or analyses that detect a failure mode or associated cause. For the sake of example, let's pretend we haven't implemented a detection mechanism for our contactors yet. Next, assign a detection rating. Here is an example of a detection scale. I don't like this one very much because it's so subjective, unlike the severity and occurrence tables in the previous slides, which came from the same source. I'd rather see less ambiguous definitions, ones that give some hint of the difference between remote and low. I would prefer perhaps to define how quickly the fault will be detected, or in what percentage of units. In our present example, since we have no detection mechanism in place, the detection rating is a 10. Put that 10 in the table. And now we multiply the severity times the occurrence. That's called the criticality. And then multiply the criticality by the detection rating to get the risk priority number, or RPN. Phew! We've completed one row of the DFMEA. You can see how intensive FMEA is. Let's zoom back out to the overall table for perspective. This is what we've filled in. It would be tedious to fill in the rest of the table in this lecture. So let's pretend we've filled out the whole table, pretend that it's properly completed. Now what? The criticality and RPN allow a ranking of potential failures in the order in which they should be addressed. In this case, we'd probably see the contactor welding shut near the top of the list. Top of the list means top priority. Let's consider how we might address this situation. A good option is to define and implement a diagnostic procedure to detect when a contactor is welded shut, designed to run for every contactor use cycle. I admit I'm just making up a detectability value, but it for sure will be less than the 10 we had before. So now we can update our table, and perhaps the contactor welding shut is no longer our top priority, and we move on to mitigate the failure with the next highest criticality, or RPN. To summarize what we've learned about DFMEA, it is a quantitative analysis starting with the system or component requirements. It forces thoroughness. A good FMEA requires a good understanding of the system, and thus would best be done by an interdisciplinary team. In practice, it is such a time-consuming effort that a dedicated safety engineer usually runs it, supported by occasional check-ins with the design engineers. FMEA reflects the severity and probability of events, and in that, goes beyond fault tree analysis. It is most useful for checking that nothing was missed through its very detailed process, and for prioritizing items based on which are most likely to result in severe consequences. This completes the lecture on safety in my Battery Management Systems course. If you liked what you saw, please help this course get seen. Share it with a colleague, share it with a customer, share it with a favorite college professor, and of course, subscribe, like, and comment.